Hello, everyone. My name is Chris Huxley, and I'll be introducing today's webinar. Welcome to another of the Australian Water School's free webinar series. Today's event is sponsored by Tuflo, and it's a really interesting topic. It's Water Quality Modelling Part 2, specifically modelling the environmental fate and transport of pathogens. Very interesting. We've got a presenter of Michael Barry today, and we'll have Emma McCall in the question and answer panel. Let's have a look at who's registered. In total, we have over 750 people, so it's a really broad audience, 61 countries. Yeah, thank you all for joining. It's going to be a great day. Let's introduce our presenters and panelists. Michael and Emma, can you please turn on your camera?
Hi, Chris. Hi, everyone.
Welcome, and thank you so much for taking the time to run this presentation. To start with, can you maybe tell us what attracts you to water quality modelling? Why do you do what you do?
Yeah, thanks, Chris. I've been in the water modelling field for more than 20 years, and the same thing attracts me to it, and that is that I think we have a real opportunity as professionals to better manage and interact with our natural environment. And as part of the custodianship that we all share, water quality modelling is one of the tools in that armoury that help us do that custodian job and really try to protect and enhance our natural environment, which is so important to life and the way we live.
Excellent. And how about you, Emma? Why water quality modelling?
Yeah, I think along the same sort of lines, it really interests me how the physical and the chemical interact with each other in the environment, and being able to use the water quality modelling tools to actually look at the environment as a whole and understand, what sort of the difference those changes make in the environment and how we can improve the water quality in those systems. Yeah.
It definitely impacts a lot of stakeholders, so it's a very worthwhile topic.
Yeah.
Shall we bring up the poll that has been completed? Michael and Emma, can you scroll through? Is anything that surprises you, or does it all look as you'd expect?
Yeah, that spread of sectors is interesting. Private and government and research cover most of the ground. I think, and private is about half, which sort of makes sense to me. Yep.
It looks like the volume or the larger proportion of attendees are in the 0 to 5 year bracket.
Yep, that's right. Oh, wow, we've got 15 people whose job is 75 to 100% water quality modelling. Excellent. You are my friends. But that's a pretty good spread, though. We've got, a good chunk of people. So only 30% haven't involved too much in water quality modelling. So 70% of the people attending have had something to do with water quality, which is just great. Yeah, really good.
Oh, I'm sure they'll get a lot out of your presentation and the question and answers. Shall we get straight onto that?
Absolutely.
I'll pass over to you.
Okay, I'll share my screen. There you go, Chris. Can you see that all right?
Yes, that's coming through perfectly.
Great. Excellent. All right. Well, it's lovely to be here, and really grateful for the opportunity to speak about something which I think is really important, and that is better understanding our natural environment and using the tools that we have available to us to do that. So we'll talk about water quality modelling, but we'll talk in particular about the simulation of pathogens today. So what we'll do is we'll start talking about what pathogens are, and why we care, why we're interested in pathogens. And then we'll talk a little bit about how we model pathogens with the numerical software we have available to us. And then always the interesting bit where there's pretty pictures and movies, we'll have a look at an example model, and we'll see some of the things we've talked about in the first 3 dot points we'll talk about and demonstrate in the final dot point there with an example model. So what are pathogens? Well, they're microbes, and all pathogens are microbes, but not all microbes are pathogens. So there's good and there's bad microbes as far as we're concerned. And the ones that have an effect on us and the environment, which is deleterious or negative, we typically call pathogens. And those are things like viruses and bacteria, and they can be either single or multi-celled eukaryotes. And as you said, they can be beneficial and harmful because there's so many of them, and they're everywhere. Like on Earth, there's supposed to be somewhere in the order of 10 to the 31 organisms. That's a 1 with 31 zeros after it. So they're everywhere. And so there's a diverse range of microbes, and some of those are pathogenic. Some of those have a negative effect on us in the environment. Just to have some idea of how many pathogens, or sorry, how many microbes there are on the planet, if there's 10 to the 31 organisms, that's 10 billion times more than the number of stars in the universe. So it's a big number, and they are everywhere, including with us. And so each human, we have around about 30 trillion microbes as part of who we are. And again, some are good and some are bad. We have in the majority good, but sometimes we come across the bad microbes with the pathogens. Some familiar pathogens that we might have come across in the media or in our work or talking with people: measles, smallpox, Zika and Ebola viruses, and of course SARS and COVID have been in the news a lot in the last few years. They're typically associated with human health, of course. Some pathogens that we might hear a little bit more about in the natural environment, particularly the aquatic environment, which is what we're talking about today, include things like cryptosporidium, or crypto as it's often referred to, and that's clearly not the currency. It's a pathogen. E. coli is commonly talked about in the media, and as is norovirus and Campylobacter. Campylobacter is called Campy. And I've certainly traveled around the world, and I've been subject to many of these over the years, and they can be very unpleasant and really can cause human disease quite widespread. And we care about this because latest statistics tell us that about 20% of global deaths, at least in 2019, pre-COVID, of course, were a result or could be linked to pathogenic infection. So we care. We care a lot about these pathogens, and we care about minimizing their impact on our lives and the environment. Of course, this is a human cost, which we suffer as a result of pathogens, but there's also an economic cost. And of course, numbers vary depending on where we look. But in 2019, 2020, pre-COVID, estimates are that about $1 billion a year is the cost of pathogenic related disease just in the US. So there's some big numbers out there, and we really do need to be making sure that our exposure to these pathogens is minimized or eliminated, and certainly managed to reduce the deleterious effects that these things can have on people and the environment. So whilst we've talked about COVID and all sorts of viruses and pathogens, today we're really focusing on environmental waterborne pathogens, and that's the cryptosporidium, E. coli, norovirus sort of types of pathogens that are often looked at with numerical tools. But where do these come from in the environment? It's all very well to say that they're there, but where do they come from? Well, I guess one of the key sources of pathogens that affect us is from human waste, and that human waste is delivered into the environment by a number of mechanisms. This is not an exhaustive list here, but it's some of the mechanisms, and sewer overflows or leaking sewers can deliver pathogens to the environment, particularly when it rains. Sewers can become overloaded, and they can either increase their exfiltration of pathogens into the environment, or they can overflow entirely, either by design or not. Combined sewer overflows is often by design. In other cases, the design isn't there for these sewers to overflow. We might have manholes popping and sewerage entering the environment in that manner. And of course, on-site sewage treatment systems do also deliver pathogens to the environment, particularly if they're not functioning as designed or not working well or haven't been maintained. They can most certainly deliver pathogens to our surrounds. So that's the human waste side of things. The mammalian waste is also a source of pathogens, and this is both in the agricultural and urban settings. So in the urban settings, we might be thinking about dogs and those sorts of mammals in the environment. And in an agricultural setting, we could be thinking about sheep and cows and pigs and those sorts of things, and their waste entering the environment, particularly through waterways. And those pathogens, once have entered the waterways, is what we're talking about today in terms of our understanding and modelling. So these pathogens are released, human or mammalian waste. Where does it go? Well, clearly, surface discharges of pathogens from the mechanisms we talked about could end up in freshwater creeks and streams and rivers and lakes, and we'll look at a lake a bit later on. But pathogens can also end up in reservoirs, including water supply reservoirs. So there's a clear linkage there between delivery of pathogens and re-receipt of those pathogens if the drinking water reservoirs are involved and people are actually consuming water downstream of these reservoirs that have been impacted by pathogenic delivery. So that's something that's of key interest. And natural and urban lakes obviously receive pathogens from surface flow. Groundwater flows can also be impacted by pathogens, particularly on-site sewage treatment systems that might be not operating as designed, can deliver those to the groundwater. But we'll be concerning ourselves with surface water today. And finally, in this list, which is not exhaustive, but finally, coastal oceans can often be receivers of pathogenic loads, and that's because wastewater or sewage treatment plants can discharge collected effluent to the ocean. There's a bit of an image there on the right-hand side, and the level to which that waste or that effluent is treated before it's discharged does vary around the world, with some discharges not receiving too much treatment at all in terms of pathogen removal, and therefore there's a direct linkage there between waste being generated on land and being delivered directly to our natural environment, with today's topic of pathogens being one of the key constituents of concern in that delivery. Other wastewater treatment plants use very high-end treatment techniques like UV radiation to kill pathogens before discharge to the environment, but not all do, because that's expensive and costly to run. So there's always that balance between how much we treat water and the impacts downstream of discharging it to all these common environmental receivers. Okay, so we've talked briefly about some pathways, but just to be clear, the environmental pathways to humans, which is what we're concerning ourselves with today, of pathogens. Again, this is not an exhaustive list, but perhaps the one that springs to mind the most is ingestion of contaminated drinking water. Some of us may remember towards the end of the 1990s, particularly in Australia, there was some instances where water supply reservoirs were thought to be receiving pathogenic loads from the catchments, and that some of these loads were moving through water supply networks to consumers. And there were boil water orders issued at various times and places in Australia during that time, and I'm sure there's been those overseas as well, where the boiling was to remove pathogens before consumption. So the number one red flag, probably of the highest priority, is about drinking water supplies and delivery of pathogens downstream, and minimisation or removal of that risk. But we don't just have to drink contaminated water to suffer effects of pathogens. There's other ways that we can interact and be affected by these. And they're given names: primary and secondary contact. So primary contact is when we have direct contact with contaminated water. So we might go swimming or bathing or water skiing or diving or whatever it is in a contaminated waterway, where we're actually in direct contact and touching the water in those waterways, and possibly breathing in vapors or swallowing the water or whatever might happen when we're making that direct contact. That's called primary contact. Secondary contact is one step removed back from that, and that's where we might be still interacting with a waterway that is potentially contaminated, but we are not directly touching the water where it sits. We're perhaps boating or fishing or canoeing or kayaking or something like that, where there's still the opportunity for contaminated water to interact with our systems, but it's not as direct as primary contact. And there's some instances on the right-hand side of this slide that that show how these sorts of things arise, and that governments all around the world are very much interested in this primary and secondary contact between humans and contaminated waterways. And then finally, consumption of contaminated food is one way that we can be exposed to pathogens. We're not talking about that too much today, but one of the common pathogens that we talk about on consumption of some particular types of food is salmonella, and that can come through contaminated food consumption. And there's an article there on the right-hand side about lettuce being linked to E. coli outbreaks. So at the end of the day, pathogens are everywhere. They're in our environment. We need to exist with them, but minimize or manage that risk that they pose to human health. So how do we do that? We know these pathogens is 10 billion times more than the number of stars in the universe, just on our planet alone. How are we going to go about managing and understanding these pathogenic pathways that lead to human health issues and economic and human consequences from those pathways? Well, there's many things we can do, but one of the things we can do is look to numerical modelling, and we would do that to minimise or eliminate risks associated with these pathogenic pathways and better manage public health. And one formal framework that has developed over the last period of 10 to 15 years is the quantitative microbial risk assessment, or QMRA. And what that really tries to do is understand those linkages, those pathways between pathogenic release and human exposure. Certainly the projects that I've been involved in that have run QMRAs have been around drinking water supply reservoirs. There's an obvious pathway there of linkage between catchment-derived pathogens reaching consumers downstream, but it has broader application than just drinking water supply reservoirs. It's a technique, as the World Health Organization screenshot shows there, about water safety management. So if you see the acronym QMRA, you'll know what it means and you know why we're doing it. And it's all about minimizing this risk, exposure risk between us and our potentially contaminated environment. The point is that numerical modelling is one of the elements of this QMRA process. Not always, but mostly it is, and it can be used to great effect within this QMRA or less formal process to try and understand these pathways between us and exposure. So how do we model pathogens? Well, we need to understand a bit about how pathogens behave in the environment, natural environment, lakes, waterways, rivers, estuaries, coastal ocean, before we can begin to simulate them, because we can't simulate things that we don't know how they behave in the environment. We need to know what drives their growth and mortality. So this is not an exhaustive list again, because this is a very complex and involved area of science that we're not pretending to go into detail today. But here are some of the key drivers of pathogenic transformation in our environment, natural environment. So there's natural mortality, and that's just pathogens like everything else that lives, that they die as well. And natural mortality is associated with the rate of death in dark conditions. So it's just death as a result of natural mortality. It's just natural attrition. In addition to that, though, we have enhanced mortality rates, which is around light inactivation. So pathogens are sensitive to light. A lot of them are sensitive to light. So if they encounter light in the environment, they can be deactivated or they can die. So we need to know something about that process and how to simulate it in order to make use of the numerical tools available to us. And of course, pathogens, like anything else that's particulate, can settle down through the water column in the environment. They can grow, they can be eaten. There's predation as well. And pathogens can actually attach and detach to sediment as well. So attachment means that a pathogen will attach itself to a sediment particle, a silt, a fine sediment, and it will then travel with that fine sediment particle through the environment, whether that's settling or resuspension or whatever. and then it can detach itself as well. So there are attachment and detachment dynamics that we need to be aware of too when we're simulating pathogens. So it's not exhaustive, but that's some of the key processes or transformation pathways we'll be talking about today. But what I'd really like people to understand is that once released from those sources we've talked about into the natural environment, pathogens respond to a whole lot of different environmental forcings. And I've listed a few here, which is temperature, the 4 bandwidths of light, salinity, oxygen, pH, organic material. A lot of things can control the behavior of pathogens in the natural environment. And we need to be understanding of what these things are and understanding the processes by which these things do, in fact, modify and alter pathogenic concentrations. So the figure on the right there is really just an illustration of all the different things, and there are more that contribute to a pathogen's life cycle in the natural environment. So we need to be aware of these and making sure that we're accounting for them, or at least knowing the limitations of our modelling if we don't account for them when we undertake numerical studies of pathogens. And importantly, I'm not pretending that this is a straightforward task, and I'm not saying that we have all the processes captured immediately. What I am saying is it's complicated. We need to be very careful about how we do this modelling and make sure that we're covering and understanding key processes. And that's really where we're going with this webinar today, is understanding those key processes. So when we do model pathogens, what do we need to do? Well, we need to model hydrodynamics, obviously, because that's water movement. But assuming that that's the subject of another webinar, we'll need to specify initial conditions for pathogens. So in our lake, for example, we need to say, to start the simulation, there's this concentration of pathogens, whatever it might be, spatially varying in 1, 2, or 3 dimensions. And we need to provide boundary inflows to our model. And this is really, the boundary inflows is really where pathogenic loads are delivered to waterways. So a boundary inflow or boundary condition might be a sewer overflow entering a river, for example, or it might be a failing on-site septic system delivering pathogens into a small lake or creek nearby, or it might be the delivery of pathogens from a wastewater treatment plant to the coastal ocean. And so overall, these boundary conditions really drive the pathogenic load of our simulated pathogens in our models, our lakes or creeks or rivers or whatever we're simulating. And we roughly think of those in terms of diffuse sources, which is from a catchment that isn't that comes from perhaps rainfall events or similar, and point sources, which are the discharges from a wastewater treatment plant or a very specific sewage, on-site sewage treatment plant. So between those diffuse and point sources, we specify the boundaries of our model, and that tells us what goes into our waterway, and then we need, the next stage is how we then model those pathogens once they're in our waterways from our boundaries. How we model them, well, there's lots of parameters. There's always parameters in water quality models, and there can be many. And there's a bit of an example over here on the right-hand side, just showing an example from the Tuflo FV water quality module, the pathogen simulation capabilities of the sorts of parameters we have to specify. This is not exhaustive and it's not complete. It's just an example that, we can easily, very easily start to specify tens of parameters per pathogenic species that we're simulating. So we need to be understanding how to set those parameters meaningfully to make sure our model is reproducing reality. Well, once we've set our boundaries and our parameters, what do we get from the model? Well, we get output concentrations, of course. And I'm confident that many people in the webinar today will be very familiar with running water quality models and producing predictions of concentrations of things, whether it's oxygen or nutrients or pathogens in a waterway, and presenting those concentrations and comparing them with measurements of concentrations that have been made in the field. And that's definitely the way that things have been done for a very long time in water quality modeling world. Build a model, predict concentrations, compare the concentrations to measurements, and try and calibrate the model as a result, and then make future predictions using the model. It's all about concentrations. These are important. We must be looking at concentrations clearly, but concentrations are the end result of multiple processes. And we talked about some of those before, whether it's mortality or light inactivation or settling or whatever it might be. Concentrations are the end result of a lot of things, a lot of very complicated processes. So in a way, when we look at concentrations, we sort of have to guess at how our system is behaving based on those concentrations. And that makes life really difficult in water quality modeling world, particularly with pathogenic simulation, which is complex. So we need to be moving beyond just producing concentrations as outputs from our models. And we really need to be moving towards looking at concentrations and diagnostics or fluxes. So we need to understand not just what the resultant concentrations are, but which processes dominated the delivery or the calculation of the concentrations that we're seeing in our model. Was it light inactivation? Was it settling? Was it natural mortality? We need to know these sorts of things so that we can understand our system by looking at fluxes or pathways that we talked about before, not just concentrations, because it's very difficult to back calculate or back understand what processes are dominating a system in terms of pathogenic loads in this case by just looking at concentrations. We need to look at flux pathways, and that's what we'll be doing a little bit of today through an example. So this is the example, and it's a large North American lake. It's about 40 kilometers east-west and roughly similar north-south at its greatest extents. It's reasonably shallow. It's only 10 or so meters deep and 1,200 square kilometers in surface area. The image here on the right-hand side is bathymetry, and dark colors are deeper and lighter colors are shallower. And it's qualitative. You just need to know that it's about 10 meters deep through here and then shallow around the fringes up here and of course the edges. We have built a model of this lake, Lake St. Clair, using two-flow FE. We have simulated hydrodynamics and advection dispersion in 3 dimensions. And then we've turned on the water quality module to simulate pathogens. And we're talking about the pathogens part of it today, not all the hydrodynamics and advection dispersion in 3D. Today, we're talking about pathogens. So the two-flow FE model has about 20,000 2D cells. And we're very, very grateful to the University of Windsor, Ontario, particularly Dr. Mohammed Madani, who built this model and has kindly shared that model with us today so that we can use it to talk about this really important issue. So thank you very much, Dr. Mohammed. We're very grateful for the use of your model. The environmental settings, very important. This gets back to boundary conditions we were talking about before and initial conditions. The boundary conditions in this model are really all about inflows from the surface. There's a major inflow here on the northeastern side, which we'll see when we run some simulation results. But there's also inflows around the edges of the lake, and you'll see some inflows on the southern edge and the northwestern side, and a few in the northeast as well here. And those fringing catchments are urban catchments. I mean, you can see the degree of urbanisation in the catchment here. This is Detroit. It's enormously urbanised and modified environment, as is this side of the lake, which is agricultural. We can clearly see the fields in this part of the lake here, lake catchment here. So we have sort of both the things we've been talking about, which is the urban inflows or urban impacts and agricultural impacts in terms of pathogenic loads in this model. Now, we talked about primary and secondary contact before. Well, this lake certainly does see some recreational use. So we do have boating and fishing and water sports along a lot of the lake, but particularly on the southern side here, there's those sorts of human interactions with this waterway. So this is an important thing to look at, and Dr. Mohammed was looking at this as part of his work. And so we need to be building a model, a numerical model, and forcing it with appropriate boundaries to then understand what is happening to pathogens in this lake. So once those inflows come in, they then leave the system to the southwest here. So it's quite a large system with big inflows, but we'll see some of those in the animations we look at shortly. The simulation we set up is for 1 month. only, and that's just because I chose to simulate for a month. And we are looking at pathogen concentrations for now. We will move on to fluxes and diagnostics as part of this webinar, but initially we'll look at concentrations just to give you a feel for what is happening in the system. And we'll look at alive or active pathogens, and we'll also look at dead or inactive pathogens, and we'll always look at the surface layer of the model here. In a 3D model, you can always take lots of different slices and sheets, but we'll just look at the surface layer as a sheet across the whole model. So we'll look at contours of pathogen concentrations, both alive and dead, in the surface of this lake. And I have it in pink writing here. This is entirely hypothetical. There's nothing real at all about this simulation. So Chris, there's no suggestion that these inflows happened in the past or are happening now or happen in the future. It's just an example, just to show what we can do with numerical models and how we can use their outputs to understand systems, nothing more. In this initial simulation, I have included light and natural mortality as ways of converting or going from alive pathogens to dead pathogens. I know there's more processes and we'll get to those, but just for the sake of simplicity to start off with, we've just looked at light and natural mortality. So what we're going to show now is some results from the simulation. And these are animations. And on the left-hand side and the right-hand side are the same zoom extents, and it's the same model, but we're presenting different results in each of the panes. On the left-hand side, we're presenting surface concentrations of alive pathogens, and on the right-hand side, we're presenting surface concentrations of dead pathogens. And this is the color scale that applies to both equally. So you'll be able to visually look at them and say, okay, well, the colors are the same on both, so I can gauge the relative concentrations of alive and dead between the two. They are directly comparable on a visual basis because they use the same color scale. So what we'll see is inflows coming in from the north or the northeast and leaving in the southwest. But I'd really like you to pay attention to what you see on the alive pane in terms of color contours compared to the dead pane and dead pathogen pane, and really contrast those as the animation plays. So I'll start that now. So there's clearly inflows coming in from the northeast, as we talked about, and there's also inflows coming in from the southern sides, as we talked about. But already we're seeing quite a strong qualitative difference between alive pathogens and dead pathogens, again in this surface layer, as the animation evolves. And what we're really seeing is that alive pathogens do not persist. They die. So the model is predicting that these pathogens, which are delivered to the system as alive, they don't persist. In general, certainly not as much as dead pathogens accumulate, which is why we saw all the red on the right-hand side of the previous slide. And that's because dead pathogens were accumulating. We did see delivery from the northwest to the south, northeast to southwest, and we did see this longshore transport of pathogens running along the south side of the lake. But we've just looked at concentrations, and that's informative and it's interesting and it's certainly visually attractive to look at and present to customers and stakeholders. We can get a lot of intuitive feel for systems by looking at concentrations, but where's our system understanding? What processes are dominating the final computation or calculation of these concentrations? And therefore, what processes do we have to pay attention to as potential managers of this system? That's where the real power of water quality modeling comes in, is this understanding of fluxes, pathways or processes, in addition to concentrations. But I think the real power that we can pull out of this model now is to look at flux pathways that deliver the concentrations that we just looked at. So was natural mortality dominating? Was light deactivation dominating? We don't know, until we start to look at those fluxes that are reported by the water quality model. So one of the things in the 2Flow-FV water quality module is that it doesn't just prepare or produce and output concentrations, it actually outputs every flux that it computes to generate those concentrations. So it will output the flux in every cell at every time step for the loss of alive pathogens to dead pathogens via light inactivation, for example, in every cell at every time step. So instead of plotting up contours of concentrations, we can actually plot up contours of fluxes. So we can plot up contours and make animations of the flux of alive to dead pathogens due to light inactivation, and the flux of alive to dead pathogens due to natural mortality. And we can compare the two and start to get a feel for the relative magnitude of the two, and therefore an understanding of what processes are important in our system. And that's really where we're going, is understanding what processes are important. Concentrations are important to understand, but processes are more important, because those processes are the ones that we want to interact with in our management of these systems. So let's look at some fluxes, or diagnostics as we call them. It's the same model run. We're not presenting concentrations now, we're presenting fluxes. And we will look at the light deactivation fluxes and the natural mortality fluxes in the animation on the next page. And we'll plot those as surface contours, and the units for those fluxes are CFU, which is a colony forming unit per 100 mil per day, on both in the same color scale again. So again, it's a per day rate. It's a flux. It's a flux of pathogens, not a concentration, but a flux. And just for the record, if you look at the color scale in the next slide, a positive flux is from alive to dead. And that's just a convention that we follow. So we're not presenting concentrations, we're presenting fluxes. And on the left-hand side, we're presenting the flux, or the death of pathogens due to light inactivation. And on the right, we're presenting the flux or death of pathogens that are alive due to natural mortality. So this is from alive to dead due to light on the left-hand side, and this is alive to dead due to mortality on the right-hand side, and they're fluxes. So let's play this and see what we come up with. So we know that there's lots of pathogens being delivered from the northeastern inflow, and the animation on the left tells us that those pathogens are actually being converted from alive to dead to quite some spatial extent, as opposed to on the right-hand side, where the natural mortality of pathogens is really confined to some quite small areas compared to the light inactivation. And I'll play that again to pay attention to this pulsating, or pulsation in the video on the left-hand side. That's obviously occurring because light is only around during the day, not during the night, and so there can be no death of pathogens during nighttime, which is why the color contours come and go. That's because it's day, night, and we'll look at that in more detail shortly. But I think already we can get the qualitative sense that perhaps light inactivation might be a more important process than natural mortality in this system. Certainly it took up a greater area, and there was bigger blobs of red with the light inactivation compared to the natural mortality. And we'll look at that more quantitatively later, but it's a really important insight that we've understood now, that we'd better start paying attention to how we parameterize light inactivation in our model, because it looks like it's a fairly important process the way the model is configured. And in fact, light inactivation is orders of magnitude greater than natural mortality. And we'll look at some figures in a minute to demonstrate this. But having identified that in this particular configuration, light inactivation is a dominant flux pathway, that generates concentrations of pathogens, and that's fine. But having identified the dominant flux pathway, we'd be really certain that we're getting that parameterization right and being defensible about how we parameterize pathogens in that process as a result. So we looked at two processes. Let's just add in a third, which is settling, which we talked about. And that's just pathogens because they're particulate-like. They can settle down in the water column during the day and night equally, and settle out on the bed and not reappear. So in this simulation, I've turned off resuspension of pathogens just for the purposes of this webinar. But I've applied a typical settling rate equally to both alive and dead pathogens, because they settle whether they're alive or dead, it doesn't matter. But what we'll do in the next animation is we'll compare the settling fluxes again with light inactivation fluxes again, because we found that light inactivation was the most important flux from comparison with natural mortality. Now we're going to compare that more important flux with settling. And again, a positive flux is from the water column to the bed, so a disappearance. So on the left-hand side, we have exactly the same animation we showed last time, which is the flux due to light inactivation. And on the right, we have now a new figure, which is the flux due to settling the pathogens through the water column. So I'll play that and you'll see the pulsing again on the left-hand side, which we talked about. But you'll notice on the right-hand side that, again, the fluxes due to settling are localized. There's red there, there's red blobs for sure, but they're much more localized than the mortality or the inactivation due to light. And that sort of tells us again that maybe settling is not that important, and maybe light is still the dominant process. And in fact, that's true. And we'll look at a figure in the next slide that demonstrates that. Really, settling doesn't really matter compared to light inactivation. But we've reached a point now where we need to stop just looking at contours and coming up with qualitative assessments. We need to start looking at some processes and pathways more quantitatively. So we'll do that using additional two-flow FV outputs. So one of the things that two-flow FV will output is the mass across the whole domain at a particular time step in the model simulation of something. It might be oxygen, it might be salt, it might be nitrogen. In this case, it's pathogens. So two-flow will output the mass, the entire mass of pathogens in this lake at each time step. So we can plot a time series of mass of pathogens as the simulation unfolds. So it's like a summation across the whole domain of pathogens. And we're presenting not a concentration and not a flux, but a mass. And this is what it looks like. So here's a simulation, which, as I said, is more or less a month. This is time on the horizontal axis, and this is on the vertical axis is the mass of alive pathogens in the whole two-flow model at a particular time, or at every time. That's what this line is. And we can see straight away that there's some very interesting features to this time series. So after we start our simulation, we've got a little bit of variation in total mass, but then what happens? Mass increases greatly. That's when we started seeing inflows coming in from the northeast side, as we saw those pulsating inflows. This is delivery of a large pathogenic load to the model domain, and that's why that number goes up. But then what do we see? We see this sort of sawtooth, jagged behavior of the total number of pathogens in the model over time. Why is that? Well, let's compare that on the same figure to PAR, which is photosynthetically active radiation. It's shortwave radiation, it's sunlight, it's visible light, it's what we see. And this is the time series of visible light that was applied to the model. And we can very clearly see that there's a correlation between the two. So if I pick out a couple of random locations, when pathogen concentrations drop dramatically, that's when it's during the day. And that's when the radiation is high and has peaked. So this is another way of saying, yeah, actually, we think that light inactivation is pretty important in this model, because we're, in some cases, dropping by a factor of 5, from 2.5 down to more or less 0.5 in a day as a result of light inactivation of these pathogens. And it happens time and time again. And that's a really nice quantitative or more quantitative support for what we'd observed qualitatively in animations before. Now, if I add one more line to the same plot, this dark blue line, this is the same mass of pathogens computed by two-flow FV, but in the settling model instance we looked at before. And we can see that most certainly the dark blue line is lower. There's less mass of pathogens in the model at a given time in the settling on simulation compared to the light simulation, but really it's not very much. In the scheme of things where our light inactivation is causing substantial decreases in concentration, a settling is not, mass, a settling is not really changing mass by that much. So again, that's consistent with what we observed before. Settling is not that important. Now, finally, and this is the second last slide, I ran a simulation where I completely turned off light inactivation of pathogens. And that's the resulting mass as a function of time is this purple line. So it's obvious that when we turn off light inactivation, we get a whole lot more alive pathogens in this model because they're not dying by the primary pathway, which is light inactivation. So to wrap up, what have we learned? Light inactivation is the most important process. We better get that right when we parameterize it, is the message. To promote understanding, rather than just looking at concentrations, to promote understanding, we've used two-flow FV diagnostics, which is the fluxes, the light fluxes, the settling fluxes, and the natural mortality fluxes. And we've used two-flow FV mass reporting. And we've really looked at multiple lines of evidence to help us interpret concentrations, which are very difficult to interpret without those fluxes behind them. And this doesn't just apply to pathogens, in my view, this applies to water quality modeling in general. We need to stop guessing. Don't guess about why a concentration is doing what it is. Let's look at the fluxes and the diagnostics that cause those concentrations to understand how a system works. So last slide, modeling pathogens is no simple task, and I haven't intended to pretend that it is simple, but we need to really, I think, look at process understanding in our simulations, and that means looking at fluxes, not just concentrations. And it applies equally to large and small systems, whether it's Lake St. Clair or whether it's an urban wetland. These principles apply. Let's look at concentrations, but let's understand why those concentrations are being predicted by looking at flux pathways and processes. And that's all from me, Chris.
Excellent. Thank you, Michael. That was brilliant.
Pleasure.
Emma, if you can turn on your microphone and video, if you can lead the questions, that'd be really appreciated.
Yeah, thanks, Chris and Michael. There's been a few good questions that have come through during that presentation. So I've got a couple that I've saved here for quite a long time, so I can actually ask you them.
Very good.
This one's got a few components to it. So I'll read it all out and we can sort of step through each one as we go.
You'll need to remind me of the components after you've read it all out.
Absolutely.
I forget stuff. Yeah.
All right. First of all, how do you model the pathogen transportation? Is it a Eulerian or Lagrangian model?
Yep.
How have you solved the radiation? And
Yep.
how do you tackle the large timescales in the system?
Great. Okay. First one again.
First one again. How do you model the transport? Is it Eulerian or Lagrangian?
Yeah, it's Eulerian. Yeah. So we are for the moment assuming that pathogens we are simulating them as dissolved quantities. I know they're not dissolved quantities, but that's how we simulate them in the Eulerian field at the moment. The next release of the two-flow FV water quality module will allow for simulation of pathogens and other things as particulates, and we'll actually use the sediment transport module in two-flow FV to simulate the detailed settling and resuspension and bed load behaviours of pathogens. But for now, it's Eulerian. Emma, the second one was?
Have you solved the radiation? And
solved.
Maybe, so how have you solved, have you solved the radiation? How have you solved, I guess is how I read it. So yes, maybe a bit of explanation on what that means in terms of pathogens.
Yeah, totally. So what we do is we have built-in tools that allow us to pull atmospheric boundary conditions, which are air temperature, humidity, rainfall, wind speed and direction, and radiation from global atmospheric models, and we can choose a range of those. And so a boundary condition that is applied to the lake model has got forcing from those global atmospheric climate models for all those parameters I just mentioned. Once that radiation hits the two-flow FV model, that's when two-flow FV takes over, and it says, all right, I've received this radiation from the atmosphere. That radiation is going to decrease in intensity as it moves down the water column, because we know that light is attenuated through water columns, and two-flow FV does those calculations. And that attenuation is based on local conditions which are dynamically simulated, which include sediment concentrations, organic concentrations, and general background absorption of light properties. So that light field that is computed and attenuated by two-flow FV is the light field that is applied to the light inactivation of the pathogens. So pathogens that are at the bottom of the model, they're not going to be as greatly affected by light inactivation, because by the time the light gets to the bottom of the model, it's much less intense than at the top. So that dynamic simulation of that light impact is what 2Flow FE will calculate based on being forced from a third-party global circulation model.
Yeah, great
And I should
answer.
say that we separate those into 4 bandwidths, which I think I mentioned was light, visible light, UVA, UVB, and infrared.
Yeah. Excellent. The last part, how do you tackle the large timescales involved in this system?
Excellent question. Excellent question. And it's the perennial water quality modeling question, which is, we are asking questions typically at a range of timescales. So in a reservoir, a water supply reservoir, we might be interested in only modeling pathogens in one particular inflow event that might last for 2 days, say, because we know that inflow event is going to insert into the reservoir and then make its way through the reservoir to the water supply offtake and potentially contaminate water downstream. So it's a very short time scale that's eminently achievable by most models these days. The real challenge is when you look at large systems like St. Clair or the coastal ocean, for example, where simulations are asked questions that are annual or even decadal. And that's where computation becomes a potential issue. Computation time. So what we've done is we have launched 2Flow FE onto GPU compute. And that means that we can use graphics processors instead of CPUs or central processing units to speed up our simulations. And with the latest cards, the GPU cards are out there, we can get 40 to 100 times faster simulation than we could on CPUs. So we can go from simulating a day to simulating 100 days, but do it in about the same time if we run it on a GPU, a CPU to GPU. So definitely understand the problems with long-term simulations, but we're doing everything we can to get over those barriers. One of them is GPU compute, the other is cloud compute. So we can now push our models up into the cloud and access the best Amazon web services or whoever, Azure web services in terms of their really fast cards. We can access those too.
Oh, thanks, Michael. A couple of other questions have popped up if we've still got some time there.
Yeah, indeed. Yep.
Do pathogens have any relation with the nitrogen or carbon cycle? So any of the nutrient cycling that's also happening?
I think if we looked at boundary conditions inflows to models, we would probably see a correlation between pathogenic load and carbon and nutrient loads, because typically pathogens are part of organic waste. So we would probably see them go up and down on the boundaries as inflows to our models, just because of the obvious connection between the matter that contains pathogens and the pathogens themselves. Once the pathogens are in the model domain and 2Flow water quality module is doing those calculations, there's less interaction with nutrients and there's more interaction with organic matter. And that's because there's some research out there that says that the ability for pathogens to survive in organic matter-rich environments changes as those organic concentrations go up and down. And that's due to a whole lot of factors, including light, but also as a food source. So I think there's more of a scientific connection between pathogens and organic material inside the lakes. We didn't look at those today, but they are certainly known. They're also known to be very tricky to simulate too. So again, I'm not pretending that we're doing all this marvelously. It's really about picking those processes that we think dominate a system and modeling accordingly. Yeah.
Yeah, great answer. I think that sort of answers probably most of the questions that have been left in there. It's really good to actually see how you've been using the diagnostic tools to really work out what's going on and what's impacting I guess it's the growth and the death of those pathogens in there. And that will be a really useful tool moving forward and a way at looking at modeling differently.
Yeah, I think it's really important, Emma. And certainly over my career, 20 years ago, all we talked about was concentrations, and we compare them to water quality objectives and toxicity trigger values. And we would never really think about what processes generate those concentrations. So One of the things that we've done in building the water quality module with 2Flow FV is really giving users access to those diagnostics or those fluxes so that they can do their own mass balances on the system. They can understand what those dominant fluxes are. One of the things that we did quite recently, if you can still see it on my screen, Emma, can you see the web browser now?
No.
Not yet.
Yeah, I'll have a look. I'll just reshare that. That's all right. Okay, there we go. Here we go. So
Yes, coming through now.
So just as something that we've done in response to questions from our users and industry is we've put out an insights paper, which we do often in 2Flow, and the one we wrote just a little while ago was about using diagnostic variables to speed up your water quality calibration. Because I think the hardest thing in the world is trying to get a water quality model to calibrate just by looking at concentrations, because we don't know what parameters to change in our model to change a concentration in comparison with a measurement. We just don't know unless we look at those diagnostics or those fluxes. So we can save ourselves a whole lot of time and money and follicles, in my case, if we look at these fluxes in our water quality modeling and calibration process, rather than just trying to compare concentrations with measurements. So in this particular insights article, well, I looked at a bubble plume design in a reservoir, and really all I said is, well, we've set a model up of this bubble plume, and we've plotted with depth and with dissolved oxygen concentration. We've plotted a model prediction in pink versus actual measurements in the field in blue dots. And of course, the first time we run a model, we never reproduce what happens in reality. Of course, we need to always calibrate our models. But the question arises, well, this is oxygen concentrations. What do I do? What do I do to get that pink line lining up better with the blue dots? I don't know. I could do any number of things because dissolved oxygen concentrations, which is this blue box, they're affected by atmospheric aeration and sediment flux. And sediment flux is affected by dissolved oxygen and temperature and dissolved oxygen concentration. So all these processes are parameterized. Where do I start? I don't know. And I don't want to guess because it's going to take me a long time and it's going to be very expensive. We don't want to do that. We want to actually understand these fluxes into dissolved oxygen and out of dissolved oxygen that contribute to this calculation of a concentration. And once we understand those fluxes, then we can work out what parameters to use and we can better calibrate our model. So I just go ahead and I plot up the fluxes in time. This is in time, my simulation in hours, and this is dissolved oxygen fluxes. These aren't concentrations, these are fluxes. Here's the atmospheric flux, which sort of peaks when it's windy at 1,000 milligrams meter square per day. But here's the sediment flux. So they're very, very different magnitudes. The sediment flux is like 5,000 milligrams meter squared per day, and the atmospheric flux is not very much unless it's very, very windy up here. So this tells me immediately by looking at the fluxes and the diagnostics that I should be paying attention to sediment flux, because that's what's taking all the oxygen out of the model. So once I've done that, I can actually go ahead and use the 2Flow water quality manual to look up the equations that govern that flux calculation. I can see the parameters that I specify in those equations. And I can also interact dynamically in the water quality module. I can interact dynamically with some figures that have been set there to help me understand how those parameters and their effect is on dissolved oxygen. So if I just go to the water quality manual, which is all online, of course, if I search for oxygen sediment flux, and I go to oxygen, I can go directly to a figure that shows me how sediment flux varies with this half saturation concentration for oxygen. I can move the slider backwards and forwards, and I can really understand what a value of 2 means for this parameter in terms of sediment fluxes. And that means, again, that I'm not guessing. I'm not saying, oh, what if I change it this way or that way? I know what to do because I've used the interactive tools in the manual. So once I've done that, I can adjust those parameters. I can rerun the model and I get this blue line for sediment flux instead of the pink line. And look, my calibration now with the green line or the blue line matches the dots because I've measured, I've known exactly what parameter to change because I've looked at fluxes and I've used the tools in the manual to improve my calibration. So instead of guessing, we've actually used the tools that are available to us in terms of fluxes to improve our model performance and run a simulation with the diffuser or the bubble plume diffuser turned on to get really nice oxygen concentrations in depth. So instead of guessing, we use the tools available to us, and that's all I've been saying in the webinar today about pathogens. That's more or less it.
That's really powerful, Michael.
It's fun. I like it. You can probably tell I like it.
When I read that article, I had a real light bulb moment. So it's yeah, a really excellent article.
Good.
We're right on the hour, so it's actually a really good time for us to finish up.
Great.
So thank you everyone for joining us. We'll see you in, I think, 2 months' time is the next 2Flow webinar.
Awesome.
Until then, goodbye.
Thanks everyone. See ya.